Hello and welcome back to the lectures on high performance scientific computing. We will go further in our discussions into OpenMP programming today. The credit for the slides again go to the Argonne training program on Exascale Computing 2024 from the Argonne National Labs. So today we will first look at the memory model of OpenMP and we'll see how variables are being handled physically in the memory. And we will then try to see how to sort of synchronize different memory elements and what is the care that we need to take while programming. So going back to looking at the simple architecture of multi-core CPUs, you'll see that there are multiple cores which have control units and arithmetic logic units. Each of these cores will have their own registers, own last level caches, then a shared last level cache, and then finally they're connected to the shared memory, which is a dynamic random access memory. Now, what's going to happen is that all these threads which are being scheduled on these multiple cores, they will share the same address space. But now just let us consider some variable gamma. Now, there are multiple copies of this variable gamma and they might be present at different levels of cache or in registers. And it's quite possible that while gamma exists in each of the registers, caches, or the last level cache, they might all have different values. So during any computation, what value of gamma should one thread actually use at any point? This becomes a big question of contention and also of coherency. So in order to have a consistent memory model, you need to provide the rules for which you can answer this question, which value of gamma that needs to be used or supplied. Now, most multi-threading programming models, including OpenMP, have some sort of a relaxed consistency. That is, the threads have a temporary view of the shared memory and that is not consistent with some other threads. The temporary views are made consistent only at certain points of the program where synchronization takes place. One of the operations that enforces this consistency is called the flush operation, and we need to understand where flushes take place. So what is essentially a flush operation? A flush operation is a sequence point at which a thread is guaranteed to see a consistent view of memory. Okay, so this essentially applies to a set of shared variables visible to a thread where the flush is being encountered. At this point, all the previous read and writes by this thread have been completed and are visible to other threads. And no subsequent read writes by this thread has yet taken place. A flush operation is similar to a fence in any other shared memory APIs. A good example of a flush is in this snippet of code. Here, if you look, the variable a is being forced into a flush. Here, essentially what is happening is that the variable a, which is being assigned a value by the function compute, when the flush call is being made, essentially all the threads are to see the most recent value of a. So essentially all parallel threads which are looking at this value will now look at the most recent value. So if you want to send a set of variables, you can use the flush directive. So the question is, what is the big deal about flush? Now, we know from our earlier lectures that compilers will reorder instructions while implementing a program. This is essentially to keep the hardware level parallelism going so that the many functional units are utilized properly to hide all the memory latencies that occur in fetching data from different levels of cache. Now, explicit barriers typically force the compiler not to move instructions beyond a certain point. Compilers also cannot move instructions past a flush on variables. But compilers can move instruction past a flush of list of variables as long as those variables are not accessed, whereas a barrier is a little bit of more of a hard stop. So keeping track of consistency when flushes are used sometimes can be confusing, and you have to be very careful whenever you're using a list of variables which are being flushed. One thing that you need to be aware of is that a flush operation usually does not synchronize with different threads. It just ensures that the thread's variables are consistent with the main memory. So what do you mean by that? It essentially means that all the different lower levels of memory are consistent with the higher levels of memory, like the random access memory. So there are some implicit flush operations during OpenMP synchronizations. This happens at all the entry and exit of parallel regions, at implicit and explicit barriers, at entry and exit of critical regions, but not generally during work sharing regions. So if you want to write code with explicit flushes, please be very careful because it's quite easy to get them wrong. But it also gives a level of control to the programmer to exploit more performance. Now, so far we have been looking at parallelism where the tasks are more or less regular. For example, splitting a for loop. Now we will look at irregular parallelism where the tasks are not of uniform length. So typically a problem becomes irregular when one of the two hold. If the data structures are sparse and involve a lot of indirect memory references, then the problem becomes irregular because we are not sure of how long it will take to access certain data members. And if the control sequences or the control structures in the program code are not your basic for loops and rather have some conditionals, then you will have some sort of irregular parallelism. One of the biggest examples of this is traversing linked lists. So if you look at this snippet of code where P is a pointer to the list head, and while P does not become null, if you have to process this pointer P and you keep looking at the next element of the linked list P. So while we're traversing this linked list, we do not know how big this program is. We cannot, neatly parallelize it using for loops. So this is an example of irregular parallelism. And this makes things life hard in the OpenMP world. So how can we go about doing this? So let's now look at a program which is using the linked list approach to compute a sequence of Fibonacci numbers at each node. And we will parallelize this program using the following constructs, which are OMP parallel, OMP for, OMP parallel for, OMP reduction, OMP critical. We will use inbuilt OMP functions like OMP get num threads, OMP get thread num, OMP get w time, and then we will also use scheduling. We will also declare variables to be private, first private or default. Okay. So here is a program of linked list with OpenMP where we have not used the task construct. So here what we are essentially doing is counting the number of items in the linked list first. Then we are copying the pointer of each node into an array, and then we are processing it. We are doing some sort of static scheduling over here where each thread is given one member to work with. So when I schedule this program with either one or two threads, if I do default scheduling, I can get this program to run in about 48 seconds. If I have static scheduling with about 45 seconds. If I use two number of threads, i.e. I have parallelized it using two cores, then the default scheduling takes 39 seconds, but with the static scheduling, I'm able to do it in 28 seconds. So this is being done without the tasks directive. Now, what we need to understand are tasks. Tasks are essentially independent units of work. Tasks can be composed of code to execute or the data to compute with. The size of each task might actually vary depending on the code that they are executing and also the nature of data that they are working with. What we are essentially doing is that threads are assigned to perform the work of each task. So on the right side, if you look at it, there are 3 tasks which are denoted by 3 different colors. If you are going to do a serial code, each of these tasks would have to be performed sequentially. But in parallel, each task is now assigned to a different thread and the thread may execute the task immediately. The threads may also defer execution until a later time. And you can see how these threads are executing these 3 separate tasks in parallel, which are generally not in the same synchronicity. So the task could construct a structured block of code, and inside a parallel region, a thread which is encountering a task will package that code block and its data for execution. Tasks themselves can be nested. A task may itself generate further tasks. Now, we will first go through what a single work sharing construct is. The single construct denotes a block of code that is to be executed by only one thread. And it is not necessary that this thread has to be the primary thread or also what was known as the master thread. A barrier is automatically implied at the end of the single block. You can remove this barrier if you would like using something called as the no wait clause, for which we will look at an example later. So what do we actually mean? If you look at this snippet of code, you see that we are starting a parallel section, and in the parallel section we have one function which says do many things, and then the function do many things can be executed by multiple threads. Then we have a single clause or a single work construct where the function exchange boundaries is to be done only by a single thread, and then subsequently you have another function do many other things which is being done by different threads in parallel. I must point out that there is an implicit barrier at the end of the exchange boundaries function, which is denoted by the curly braces, because the single block has an implicit barrier at the end of this. So how does this task derivative look now? So I have a snippet of code where first I create some threads using the hash pragma OMP parallel. Then one thread packages all the tasks that need to be done. It could be any thread. And then subsequently these tasks are assigned to be executed by any thread in some order. And each of these tasks are, one is the function Fred, the other function is Daisy, and the last function is Billy. All these tasks have to be complete before the end of the single barrier and they are released. So essentially what this block of code is doing is that the single thread packages 3 different tasks, but the tasks themselves are now being executed by different threads. Which threads? We do not have control over it. This is taken care of by the operating system. Now here is a simple example that we will walk through. We want to write a program that will randomly generate one of these 2 strings. The first string is, I think race cars are fun. The second string is, I think car races are fun. So we want to write a code which will randomly generate one of these 2 statements. So how do we go about it? The first thing that we need to figure out is that there is only one indeterminate part of the output. Whether we put the word race before car or whether we put the word car before race. Ironically, this is also called the race condition. It occurs when the result of the program depends on how the operating system schedules the threads, and it cannot be determined a priori. There is no definite output for this program. It is one of the 2. Now, a data race is when threads race to update what is called as a shared variable, and this produces race conditions. Now, ideally in mathematical operations, you do not want a race condition, this is one of the simple programs where we are trying to create a race condition. Okay, so usually programs which contain data races are undefined. Now, how do we go about creating this program using OMP parallel, OMP task and OMP single? So here is how we go about this solution. Firstly, we have to print out I think, and this is being done serially because only one thread is going to print the string I think. Then we have a parallel section. In the parallel section, the single thread will now create two tasks. One task will printf the word car and the other task will printf the word race. Now, since each of these tasks will be assigned to different threads, we have no guarantee which task will be completed first. It could be either of them. So, the behavior of this program is a little bit undetermined. So, it's quite possible that after the first I think, either the word car appears or either the word race appears. And the second word that might appear could be vice versa. And then finally, you have the printf s and rfun which are being done serially. So, there is an implicit barrier at the end of the single word construct. So, essentially what we are going to do is that we are going to print out I think serially, either the word car or race and then the word race or car indeterminately, and then s rfun. So, you have a situation here where the program definition is not quite clear and you could randomly get the string I think car races are fun or I think race cars are fun. So, when you are doing the task word construct, we have to worry about how the data is scoped. The variables in this case could be shared, could be private or could be first private with respect to the task. And this is slightly different when you compare it with threads. Now, obviously, if a variable is shared on a task construct, the references to it inside the constructs are to the storage with that name at the point where the task was encountered. If a variable is private on a task construct, the references to it inside the construct are to the new uninitialized storage that is created when the task is executed. And if a variable is first private on a construct, the references to it inside the construct are to new storage that is created and initialized with the value of the existing storage of that name when the task was first encountered. So remember, we have to see about when there's a status of the variable when the task is being encountered and not when the shared private or first private is being declared in the parallel section. So the behavior you want for tasks is definitely usually first private because a task may not be executed until quite later or the variables may have gone out of scope. Now, the variables that are shared in all constructs starting from the innermost enclosing parallel construct are shared by default. So if you look at this snippet of code where I declare OMP parallel shared A private B and then I have a task OMP task int C compute A, B and C. In this case, A is shared, B is actually first private and C is private for each of the tasks. So now let us look at how do we traverse linked lists and especially look at computing a sequence of Fibonacci series. So what are we going to do with the list traversal? So when we have a list traversal for a linked list, we have to say that only one thread will package all these tasks. So where P is now being assigned the list head, the address where P starts, and we make a copy of P when the task is being packaged using the construct first private P. Now each of these tasks are now being assigned to different threads using the hash pragma OMP task, where some sort of process is being done on P, and then we get to the next element of the linked list using P next. When or what locations of the code are the tasks complete? At thread barriers, all tasks that are generated inside a region must be complete at the next barrier encountered by the threads. So, for example, tasks generated inside a single construct, all tasks complete before exiting the barrier of that single. Tasks that are generated inside a parallel region, all tasks complete before exiting the barrier of the end of the parallel region. We also have another directive called the task wait. So, what we can ask the threads is we can ask them to wait until all tasks defined in the current tasks have completed using the hash pragma OMP task wait. We have to note that this applies only to tasks generated in the current task and not to its descendants. What do we mean by descendants? Remember that tasks can generate further tasks, and those then become descendant tasks, and we apply it only to the current level of tasks. So, if you look at this example, so you have a single thread which is now creating several tasks. One is to execute Fred, the other is to execute Daisy. So, essentially when we put a hash pragma OMP task wait after Daisy, Fred and Daisy must complete before Billy starts. But this does not include tasks created inside Fred and Daisy. So, if there are tasks which are created inside the functions Fred and inside the function Daisy, those are not limited, but Fred and Daisy must complete before Billy starts. The implicit end at the end of the single construct essentially means that all tasks, including those created inside Fred and Daisy, subtasks which are created inside the function Fred and Daisy, they must be complete before exiting that barrier. If you had put the no wait clause, the barrier at the end of the single construct is no longer heeded to. This barrier is typically very expensive, so that the next barrier actually shifts to the end of the parallel construct. So, all the tasks, including those that are created inside Fred and Daisy, must be complete before exiting the last curly braces, which is the end of the parallel section. So, this is useful if you think that there are no dependencies at this point of time. Now, let us look at a simple example for Fibonacci numbers. Now, the Fibonacci numbers is computed by the series where Fn is equal to Fn minus 1 plus Fn minus 2. Now, the way we do this implementation is recursively. So, a recursive serial code would look something like this, where you have a function which calls to compute the Fibonacci of some integer n. Now, if the integer is less than 2, it returns the value n. If it is not, then we try to compute two values, x, which is the Fibonacci of n minus 1, and y, which is the Fibonacci of n minus 2, and then we return the sum of x plus y. Now, this is a very inefficient recursive implementation which takes order of 2 raised to n steps. Now, how do we implement this in parallel? Because there is recursion and because there is a lot of data dependence, we can make this into a binary tree of tasks. So, we say that hash pragma inside the function Fibonacci, we say hash pragma OMP task, and where we have a shared value of x, and x is now calling the recursive function fib of n minus 1. Similarly, for the task of computing y, we have the shared variable y. And then we say that we need to have a task wait for both x and y to be completely computed. We then in the main program have a parallel section which then calls the Fibonacci function, and the tasks are bundled by a single thread which is just fib. So, here a task cannot complete until all the tasks below it in the tree are complete, which is enforced by the task wait. And X and Y are local, so by default they are private to the current tasks. So essentially what happens over here is sort of a divide and conquer problem. The problem is split, then the sub-problem is split again, and the sub-problem keeps getting split until a solution is arrived, and then you keep merging the solutions until you get the final solution. So essentially, you need to look at parallelism in a way that whether your work can be split into sub-problems, do the work only at the leaves, and then finally do the work to sort of recombine them. We can do the same thing for computing pi in parallel, where we use the task wait and the task constructs. This would be the example of how we can do this for the computation of pi. When we look at the timing of computing pi, we had several implementations of how this is being done. The first SPMD implementation for 4 parallel threads took about 97 seconds. When we used the critical parameter, it took about 53 seconds. When we did it based the loop-based parallelization, it went to 68 seconds. And when we do it with a task-based parallelization, it takes about only 0.52 seconds. So you can see that the task-based parallelization actually makes it more efficient. But this comes at the cost of programming effort, clearly. So the way to go about using tasks is that not to use tasks for things which are already well supported by OpenMP. For example, standard do and for loops. Though it can be done, the overhead of using these tasks becomes quite big, and also the programming effort. And it's quite easy to make mistakes. So the best quality or the best efficiency of the program comes when you are able to fine-tune and control the granularity of these tasks, and this is something which you will learn as you get to know your algorithm better. Thank you.